Hello, this is Geometry, Lesson 4-1, Congruence. In this lesson, we'll be able to use a composition of rigid motions to show that two objects are congruent. Let's look at Explore and Reason. Some corporate logos are distinctive because they make use of repeated shapes. A designer creates two versions of a new logo for the bold company. Version 1 uses the original image shown at the right and the reflection of it. Okay. Version 2 uses reduced copies of the original image. So let's make a sketch of your own version. Okay, it doesn't specify exactly how it looks like, but version 1 has the original image with the reflection, and version 2, it's a reduced size with the original image and you design from them. Okay, so here's my versions 1 and 2, but make sure you have your own. Okay, my version 1 is the same shape and it's the same size, and I just reflected them to make the logo. In version 2, I reduced the sizes and made different logos out of it. Okay. So, looking at your own versions, the owner of the company says, I like your designs, but it is important that the transformed image be the same size and shape as the original image. So what would you do to comply with the owner's requirements? Which version would suit well? Version 1, right? So you're only gonna use copies of the lightning bolt. That are the same size. Okay, so what transformations can you apply to the original image that would produce logos acceptable to the owner? What kind of transformations will we use? We're only going to use rigid motions, right? So a translation, we could use translation, rotation, or glide reflection would also meet the requirement. Because these are rigid motions. And what is rigid motion? Rigid motions preserve length and angle measures. Okay, so what's the relationship between rigid motions and congruence? This is what we're going to think about in this lesson. Let's look at example 1. Understand congruence. Suppose there is a rigid motion that maps one figure to another. Why does that show that the two figures are congruent? Figure ABCDEF here has the following lengths and angle measures. And GHIJKL is the image of ABCDEF after the rigid motion. This is a glide reflection, right? Reflection, and then the translation. So translation of this reflection, right? So look at the sides. AB is 3 units wide. BC is 1 unit wide. CD 1, and then DE 2, 2, and 3. Okay, all angles in figure ABCDEF are right angles because rigid motions preserve length and angle measure. You can look at GHIJKL. You can see if the sides are equal length, they are, and all the right angles are there too. So since rigid motions preserve measures in corresponding sides and angles, the two figures are congruent. Okay, if they preserve length and angle measures, the transformation is rigid motions. All rigid motions will preserve side length and the angle measure, which means the figures are congruent. Okay, so let's look at the try question. A 90 degrees rotation about the origin maps triangle PQR to triangle LMN. Are the triangles congruent? Explain. What is a rotation? Is it a rigid motion? Yes. So would the triangles be congruent? Would it be the same size and preserve the length measures and the angle measures? Yes. Rotation, explain. Rotation is a rigid motion. So the size and shape are the same. Okay, that's how we can define congruent figures. So let's define congruence. Figures that have the same size and shape are said to be congruent. Two figures are congruent if there is a rigid motion that maps one figure to the other. Rigid motion is sometimes called a congruence transformation because it maps a figure to a congruent figure. Okay, we can use the symbol wave and equal sign to show that two figures are congruent. Okay, so since reflection is a rigid motion, the triangles are congruent. Okay, let's look at example 2. Whoops. Verify congruence. Given the triangles XYZ and ABC are congruent, what composition of rigid motions maps XYZ to triangle ABC? Okay, there is not one correct answer, but you can say you can rotate XYZ 180 degrees about point Z, and then you get this triangle, right? And then you can move the image 3 units to the right. Oh wait, this is a reflection, I'm sorry. So you're gonna rotate 180 degrees, which means you have this way, right? So that's a rotation over point Z. And then you move all the points 1, 2, 3 units to the right. And so it's a translation of 3, 0 after rotation 180 degrees about point Z. The composition of this rule maps the triangle XYZ to triangle ABC. Try number 2. Let's use the graph shown. Part A, given the triangles are congruent, what is one composition of rigid motion that maps GHJ to KLM? Again, it doesn't have to be one exact answer. You can reflect over a line and just have one reflection, but it has to be a composition. So you can do a glide reflection, or you can do a rotation. Okay, but notice that G maps to K. So this point G has to come to K, which means if you reflect it over a line, that means you're gonna have G reflected over here. So you don't want a reflection, you need another rotation. Okay, so you can do a rotation first and then translate, or you can translate and then do a rotation. Okay, So you can rotate, again, 180 degrees. So 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Okay, rotate it. And then you have there. Okay, that's going to be J prime, H prime, and G prime. And then, so this is rotation 180 degrees, right? And then you move J 1, 2, 3, 4. Wait, where's J mapping to? M. So you want to come here, right? So go down 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 units down. And then you move 1, 2 units over. Okay? So you can do a translation of 2, positive 2, and negative 10, because that's y and that's x. Okay, and then translation after your rotation. Wait, that's a big R, which is reflection. So I'm going to write a small r rotation of 180 degrees on point J. Okay. So if you do a translation first, you have to specify your point of rotation, which is going to be another point like after your translation. So you can't use J, H, G. It's going to be a different point. Let's look at part B. What is another composition of rigid motions that maps this triangle to another triangle? Okay. What about two reflections? Yes. You can do a reflection and then do another reflection. Does that work? Yes. You have two different, yeah. So if you reflect it over y-axis and then you reflect it again over x-axis, that would be again map to the same points, but then you have to translate it. So if you want to be exactly reflecting on those points, you can reflect it with specific lines like, y equals -2 and then x equals 1 line, or you can do two reflections and then translate. Okay, so why don't we, you can reflect on the y-axis, and then you can reflect on the x-axis, and then you can translate 2 units to the right, 1, 2, 3, 4 units down. Okay. And don't just check one point, check other points so that all other points are on track. Okay. So yeah. So you can do translation to comma -4 of reflection, x-axis of reflection, y-axis. Or to be specific, you can also do a reflection over x equals 1 after reflection over y equals -2 to be exactly on top of KLM after 2 reflections. Okay. So there are many ways to write composition of rigid motions. Let's look at example 3. Identify congruent figures. Given triangles ABC, EFG, JKL, which triangles are congruent? Can we find a composition of rigid motions to map a triangle to another? If we can, then the triangles are congruent by the definition of congruency, right? If we can find a transformation or a composition of transformation that are rigid motions, then yes, they're congruent. You can use translation and then a reflection to map ABC to JKL. Okay, so ABC and JKL are congruent. What about the other triangle? Okay, look at the EG. Okay, so just without thinking about transformation, ABC. Okay, this is going to map, it has to map to EFG, right? Are the sides congruent? Okay, is AB mapping to EF, and is BC mapping to FG, and is CA mapping to GE? Are all the lengths equivalent? Well, they look similar, but look at BC and FG. They're kind of different. EG and AC, they're kind of different too. So it's easy to count EF, the lines EF, 1, 2, 3, 4 units. Okay, is AB 4 units? No, you have to use the distance formula. 4 units is this one. It's a little bit longer than 4 units. Okay, if you use the distance formula, -9, 2 and -8, 6. Distance formula is square root of your x's subtracted square plus your y values subtracted square. Okay, so and the order doesn't really matter as long as you have the x values together and the y values together. Okay, so -9 and -8 together, if you subtract them, I'm going to subtract -8 minus 9, so plus 9 square, plus 6 minus 2 square, going to be 1 square, plus 4 square, 1 plus 16, so square 17. Is that 4? Square 17 is not 4. It does not preserve length. So these two triangles are not congruent. Okay, so in order to figure out congruency, you also have to look at their measures and the angles. If they're not congruent, there is no rigid motion that maps to the figure. Let's look at try number 3. Use the graph shown. Are ABCDE and JKLMN congruent? If so, describe a composition of rigid motions that maps this to that. Okay, this to this one. So first, let's check the sides. A to E is J to N. It's going to be corresponding to J to N, right? So 1, 2, 1, 2, 3. 1, 2, 1, 2. There's something wrong with that. Can you see that? Is it going to be the same length? If the slopes are not the same and the points are not the same units away, no, it's not going to be congruent. So part A, no, not all angles and segments are congruent. Okay, what about ABCDE to VWXYZ? Okay, let's look at BC because it's easier to count. 1, 2, 3 units. Okay, BC corresponds to WX, 1, 2, 3, 3 units as well. Check other sides. CD to XY, CD to XY. Yeah. And if you check all other sides, they're all congruent, and all the corresponding sides and angles are congruent. So they should be congruent. Can you find a composition of rigid motions? Okay. First, BC has to map to WX again, right? So BC needs to be mapping to WX. Okay, let's write the points. Let's match some points, okay? A maps to V. B maps to W, and C, D, E. Okay, so in order for this to come here, do you want to reflect or rotate? You can rotate or you can reflect. Okay, it's just a matter of what else can you do, right? So why don't you reflect over the y-axis, and then you get this one. Okay. Okay, this is A prime, E prime, D prime, C prime, and B prime. You reflect it over the y-axis. And then you can translate or you can reflect again over the x-axis. Okay, or why don't we reflect, yeah, sorry. Why don't we reflect horizontally? Because that one didn't work, right? So then we're gonna reflect over the x-axis. That's B prime, C prime. And that's A prime. And that's D prime. This is E prime. And that is our reflection over the x-axis. Does it match? Yes, B, C, D, E, F. The orientation match, right? A, B, C, D, E. So then we're just gonna move all the points. How many units to the left? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 units to the left. So it's a glide reflection, right? So we're gonna reflect first, right? So we're gonna translate 10 units to the left after we reflect it across the x-axis, okay? Let's look at example 4. Determine congruence. Which pairs of objects are congruent? If a pair of objects is congruent, describe a composition of rigid motions that maps one to the other. Are these two puzzle pieces congruent? Yeah. So if you rotate 1 and 2, or if you rotate just 90 degrees, right? Then this one comes here, that one goes here, this one goes down, that one goes up. Then yes, you can map this one into here. So you're gonna rotate 90 degrees. Or rotate 90 degrees. Or you can reflect across this line, right? So they're congruent. Part B, are they congruent? Just by looking at that, the thickness are not the same, right? So the sides here, the corresponding sides are not equal to each other. The frame corners are not congruent. Okay. Part C, are they congruent? Can we rotate them and figure out if they're congruent or not? Or can we reflect them? Yeah, we can do both. You can rotate, okay? You can translate the pre-image puzzle on the left, rotate the figure 90 degrees clockwise, okay? And then you're gonna reflect over a vertical line to get this one. So yes, they will be congruent. All the colors and patterns seem to match using the rigid motions. Let's look at try it. Is a pair of objects congruent? If so, describe a composition of rigid motions that maps one object onto another. Come back when you have the answers, okay? Part A. Is this congruent? Yes. How would you describe it? You can rotate 90 degrees and then translate. Okay, is part B congruent? The shapes look similar, but are they really similar? No. Look at this one. It's F. Do you see F here? No, there needs to be a square over here, not there, right? No, not congruent. Okay. Let's look at example 5. Apply congruence. A boat builder plans to connect two pieces of wood by using a puzzle joint as shown. For a successful joint, each unit must be congruent. Okay. Given unit A, what composition of rigid motions maps unit A to B? You can just glide down, right? Translation. They have the same shape and orientation, so you just slide down. So let's look at number 5. Is unit C congruent to unit A? Are they congruent? They fit perfectly, right? So yes, it's congruent, but how would we describe the sequence of rigid motions? You can rotate it or you can reflect it, right? And then reflect it again, right? But yes, they're congruent. Rotate unit A 180 degrees around its center. And then you can translate to map to unit C. Okay. So what did we learn in this lesson? We learned the congruent figures. So if two figures are congruent, a composition of rigid motions maps one figure to another. Okay, so if they're congruent, they preserve side lengths and angle measures, so you can describe using rigid motions. That was lesson 4-1, congruence in geometry. We'll continue with the next lesson in the next video. Bye.